Okay. I'm going to start with an example about the release of power series. Now, this example is just for fun, but it can also illustrate certain aspects of working with power series and why you have to be careful in doing so, or some very strange things might happen. So I'm going to show you how you can arrive at the results. 1 plus 2 plus 3 plus 4, and so on. And we know this is a divergent series. Terms don't even go to 0. But I'll show you how you can somehow arrive at the sum of all these numbers equaling minus 112. Some of you may have seen this somewhere. And although that is based using what's known about series, it's definitely not true. Although I can show you, I will show you in a weird sense that it almost is. That's what's rather freaky about this. So what I'm going to do, I can define S to be this sum. So then 4S would be 4 plus 8 plus 12, etc., the multiples of 4. But I'm going to write them underneath the even numbers. Going to do more. Right. Yes. Okay. Then I'll subtract. So on the left side, I'll have minus 3s. And then I'll have, okay, 1. And then 2 minus 4 would be minus 2. And then I get to 3. And then plus 4 minus 8, so minus 4. Plus 5 minus 6. So on. So we get all the natural numbers again, except with alternating signs. This series would also be divergent, because this terms don't go to 0. Okay. Now, this series right here, I'm going to give you a formula for it. That'd be the sum from n equals 0 to infinity of n plus 1 times minus 1 to the n. Okay.
Oh,
So this gives us numbers 1, 2, 3, 4, 5, 6. This gives us the alternating sign. So now I'm going to think of this series as a power series, except with a specific value plugged in for x. So this would be sum, it goes from 0 to infinity, n plus 1 minus x to the n, and x equals 1. The vertical bar is used to indicate that some expression is being evaluated at a certain point. So this vertical bar means x equals 1 is plugged into this. And that's what would give me this right here.
how do you have n plus 1 and then n plus 1 minus 1?
But, oh, well, this times this.
Kind of like,
Yeah, so the n plus 1 gives me 1, 2, 3, 4, 5, 6.
oh, okay.
But minus 1 to the n causes the flipping inside.
But you have 0 plus 1, then that would be -1.
Well, if n is 0, this is 1, and then minus 1 to the 0 would be plus 1.
Okay. Oh, okay.
So now I can take a closer look at this power series, just leaving x as a variable. Now, because the idea is to try to figure out what is the sum of this series for whatever x we have. Now, notice here we have, okay, it's minus x, so it's minus x raised to a certain power. But then we have that power plus 1 down here. That door's slammed. Okay. What I'll do is, yeah, I'll write this a little differently. I'm going to do an index shift. I'm going to start n off at 1. But that means wherever we see n in here, I have to replace it with n minus 1. So this would be n and then minus x to the n minus 1. Okay.
Wait, how do you get n minus?
Because I increase this, I started at n equals 0 by changing it to 1. But because I increase this by 1 to compensate, I have to decrease n by 1 in here.
Okay.
So wherever you see n, you replace it by n minus 1, and that's how you do an index shift. Anyone tell me what this is? You've seen this before, just with x instead of minus x, but what is that? N something to the n minus 1. No, this is not, this is not about series itself, but just that expression, nx to the n minus 1. You have all definitely seen this. Derivative, power rule. So, because a derivative with respect to x of x to the n is nx to the n minus 1. That's a derivative. So I'm going to write it as such. So this is a derivative of minus x to the n, but because it's minus x, I have to put a minus out here by chain rule. Okay. And since differentiation is a linear process, the derivative of a sum is a sum of derivatives, I can take the differentiation and pull that outside the sum. Now I have that. What kind of series is this? I mean, it's a power series, but other than that, what kind of a series is it? It would be, but besides that. It is a geometric series, and that is what description we need because it'll help us get the sum. So, okay, so the first term in this series would be, I would plug in n equals 1. The first term would be minus x. And then we have the r is minus x. So we have 1 minus a minus r, which is plus x. So this is geometric series. A is equal to minus x, r is equal to also minus x. We have a minus out here and a minus in here, so I'm just going to cancel those out. All right. Also, this series is going to converge if absolute value of x is less than 1. you would find that out from the
Wait, why is there negative next to the infinity over the?
here.
Yeah.
I mentioned this earlier, that we have, this is a regular power rule, but because I'm taking a derivative not of x to the n, but minus x to the n. When I take a derivative minus x to the n, I have a power rule, but then by chain rule, I have to differentiate what's inside here,
Okay,
which introduces a minus.
okay, got it.
Now go ahead and take the derivative. Quotient rule, so we have x minus over 1 plus x squared, so we end up with just 1 over 1 plus x, the whole thing squared. But this is evaluated at x equal 1. So if I were to plug in x equal 1, I would get 1 over 2 squared, I would get 1/4. So somehow, by ignoring certain rules, I have shown that this series right here sums to 1/4. So in other words, minus 3s is equal to 1/4. Therefore, s, which was defined to be 1 plus 2 plus 3, and so on, turns out to be that divided by minus 3, so minus 1/12. Okay. So here's where I went wrong, but why there's also a bit of almost correctness to it. I can't actually do that. Why is that not allowed? And the sum of this series really is this, but not for all x. So why can't I plug in x equal 1?
Is it using a geometric thing, it would diverge at 1?
Yeah, it's outside the interval convergence. Just barely, but it is. So I can't do that. However, I can, if I have x approaching 1 from below, so 0.9, 0.99, 0.999, etc., getting closer and closer to 1 from values less than it, the limit of this as x approaches 1 is 1/4. And after working this out, what I found was if I wrote this out as a series, so I'd have 1 minus 2x plus 3x squared minus 4x cubed, etc. If I plugged in x equal 1, I would get exactly this, and that diverges. But if I wrote this power series involving x, this series right here, and I would let x get close to 1, I really would get 1/4. Now, I tried to do the same thing with the original sum, like somehow express it by itself as a power series and see if I could achieve the same effect, but I couldn't get that to work. Because another key factor here is this, how in a way I'm summing in an unusual order by writing these entries, these terms for A12 here. So that's another aspect of this that leads to this strange result. But this is related to a real result that I should make you aware of. I've talked to you about 2 different types of convergence. Does anyone remember what they are? Yes, and conditional convergence. Now, one interesting aspect of conditional convergence is it's actually proved by Riemann, as in Riemann sums for integrals, that if you have a conditionally convergent series, it is possible to make it sum to any value whatsoever, any number you pick between minus infinity and infinity, just by arranging the terms in a different order. So that's the kind of chicanery that's going on here. Whereas if you have a series that is absolutely convergent, it doesn't matter what order the terms are written in and then added up, you're still going to arrive at the same sum. So. Okay.
So. I'm still confused. So we got,
Okay, so after I got to this point,
okay,
I plug in x equal 1.
okay,
So I got 1/4. But all of this was this series.
okay,
But that is equal to -3 times the series I want.
okay,
So I have -3 equals 1/4. So now I just divide by -3.
okay.
But the thing is, when you have a power series, and if you're able to figure out a formula for it by computing the sum of a series, for instance, that is geometric, like I did here, you have to be careful about when that formula is actually valid. It's only valid for whatever values of x to which the series converges. So here I tried to plug in a value of x that's outside the interval of convergence, and some very strange things resulted. So don't do that. Or at least not without a big disclaimer. Any questions about this monkey business? Okay. Now for some real stuff. Being with power series. Right. So, yeah, task of given a power series, what function does it represent, or vice versa. This section in my notes. Okay. So one thing that really helps, a lot of examples, is a formula that I used earlier today, and in many other cases, is for your geometric series. So I'll just put the formula up here. Fresh memory. So sum of r to the n from n equals 0 to infinity is a r to the n is a over 1 minus r, where a is the first term, r is the ratio between consecutive terms. So sometimes if you can recognize that a power series, a given power series is a geometric series, you can use this formula to find the sum by figuring out what is the a and what is the r. Thing is, what can happen in this case is the a or the r can depend on x. And you also keep in mind that whatever your r is, it has to be less than 1 in absolute value for this to converge. So if r is a function of x, that condition will help you figure out the radius of convergence, and therefore the interval of convergence. So, well, actually, yeah, I have nothing here but example. So I'm going to give you a function. I'll show you how to get the power series for it. 2 over 1 plus 2x. Okay. So it's worth trying to figure out if you can write this function in this form. Because if you can write your function in this form for some a and some r, then you could write it as this geometric series. Now, what's helpful here is if we compare this expression to this formula here, okay, for both fractions, they both have this one in common. So if I write this as 2/1 minus 2x, then this is equal to a/1 minus r, where a is the numerator is 2, and then r is whatever is being subtracted from 1. So it's minus 2x. So now that you have your function in this form, you can go backwards to this. And get series. From 0 to infinity of your a, which is 2. And then your r, all raised to the nth power. And based on what we know about geometric series, versus if the absolute value of your r minus 2x is less than 1, that means absolute value of x must be less than 1/2. So this right here, the 1/2, that is your r, that is your radius of convergence. What we need to keep in mind is this formula is valid almost everywhere. The only place it's not valid is when x is equal to minus 1/2, because then we'd have division by 0. But this series converges whenever x is less than 1/2, greater than minus 1/2. So we can't always write a power series of a function that's a power series for all x in its domain, just for certain ones. Any questions about this one?
We have a question like this, do we have to write like, except for at if x equals this, or
Oh, well, if I specifically asked what the domain was, then yes, but I wouldn't ask that. Right. Okay. In this case, the r turned out to be a relatively simple function of x, but it doesn't have to be. Okay, so now function we'll consider is 1 over quantity x minus 2 squared plus 4. So this we can also express as the sum of a geometric series. We just have a bit more algebra to do. What's most important is to make sure that the denominator has the form 1 minus something, whatever that something can be. So here we have a plus 4. We need that to be a 1. So I'm going to divide top and bottom by 4. So now I have one piece of a formula in place. And because it has to be 1 minus something, I'll write it that way as 1 minus x minus 2 squared all over 4. So now it's in the right form. A is equal to 1/4. R is equal to minus x minus 2 y squared over 4. So now I can write my power series. So I have my A, which is 1/4. And then my R is going to be minus x minus 2 squared over 4, all raised to the nth power. But I'd like the power series to be coefficient times x minus my center raised to some power. It's not quite in that form yet. So a little more algebra to do. All right, so here I have a -1 to the n. And I have a 4 here, but I have a 4 to the n here also in the denominator. So that would give me 4 to the n plus 1. And then what's left is x minus 2 to the 2nth. So in other words, the only terms that are non-zero are the even number terms. So what I have here are the coefficients for even n. For odd n, the coefficients will be 0. Questions how this was arrived at. Still a matter of convergence. We need absolute value of r to be less than 1. But it can only have absolute value of x minus 2 squared over 4. It's less than 1. Now I need this to be the form absolute value of x minus something is less than whatever the radius of convergence is. So I could take the square root of what's inside. I'll have x minus 2 over 2. So the radius of convergence turns out to be 2. So whatever your r turns out to be requires absolute value to be less than 1. And then get it in this kind of form, absolute value of x minus some number is less than some number out here, that number out here, that's the radius. So that was right there. Well, to give us so much fun, let's do more. So for these examples, r has been a function of x, but a has been a constant. It doesn't have to be a constant. It's whatever the first term of your series is, whether it depends on x or not. In this example, my function is 2x over 2 minus x. So we need to get it in the same format, a over 1 minus r. We need 1 minus something in the denominator. So I divide the top and bottom by 2. So I'll have x, then I'll have 1 minus x over 2. So this is the sum of a geometric series. The numerator is your a, so it turns out to be x. The r is whatever's being subtracted from 1 in the denominator, so that's going to be x over 2. So series, that would be so a x, then I have x over 2 bn.
So you just do whatever you can to get it in that form.
Yeah, whatever algebra it takes to make that happen. And this will converge. And say if and only if, because it's geometric, it has or has to be strictly less than 1. That's the value. So you fill in your r down here. That means that absolute value of x must be less than 2. So 2 is radius of convergence. What I'd like to do is write this power series so in a more standard form, because you have normally it's the sum of some sort of coefficient times x to the n. What I have here is I have 1 over 2 to the n, and then I have x to the n and a number x, so that's x to the n plus 1.
I bet that's if and only if correct.
It is if and only if, yeah. And so because it's geometric, if absolute value of x over 2 were the equal 1, diverges. Ideally, we'd like to have power series written as, again, something times x to the x minus the center to the n. So if I carry out an index shift, so I would replace n by n minus 1 throughout. So I'd have 1 over 2 to the n minus 1 x to the n. And because I'm decreasing n, I need to start at n equal 1. So here we have index shifts. All right, so at least the power series in a more standard form. That sigma really needs help. Okay. I mentioned this because there are some homework problems. And so this right here is in the form sum from n equals 0 to infinity Cn x to the n. Because some homework problems will assume a power series is in this form, or maybe it's x minus x naught to the n, and they want these coefficients. Like they may have you compute a few of them, like what is C3, C4, C5. So in this case, because we start at n equal 1, C0 would be 0. And then C1 would be 1, C2 would be 1/2, and so on. So what this example shows us is if I know how to write a certain function as a power series already, if I multiply that function by any power of x, I can easily get to power series for that new function. All it does is it just shifts the coefficients. So if I multiply this function by, say, x squared, then I have the same series, except I have x to be n plus 2. Now, actually multiplying by x is easy to handle as long as the center of your series is 0. So that's when you can just shift the coefficients down. Okay, here's an example that's a little nastier. So the same idea of geometric series applies. Okay. So my series is, or my function is, okay, 1 over x squared minus 3x plus 2. Now, but before we use this idea of trying to make it look like a geometric series, we have to keep in mind that our R ought to be, for instance, a multiple of x, or maybe a multiple of x to some power. If it's a more complicated function of x, then it's going to be difficult to get the coefficients of a power series. So we shouldn't try to take this fraction as it is and write it like a sum of geometric series. Instead, what we should do, factor the denominator. How's this denominator factor? Yeah, so x minus 1, x minus 2, and then use partial fraction decomposition. Write it as a sum of two fractions, so constant over x minus 1 plus the other constant over x minus 2. Sorry, I'm going to write it this way. It's just cleaner. And use whatever order you want, but okay. So if I write my original fraction on the left, what do you do to get a and b?
Multiplied by the original denominator.
Yeah. Okay, so multiply both sides by x minus 2 times x minus 1, so we get 1 over here. And then we're going to have a times this denominator divided by x minus 2. So the x minus 2's will cancel if you use x minus 1. And then b times this denominator divided by x minus 1. The x minus 1's will cancel. You get b times x minus 2. It's always, each constant multiplied by whatever doesn't cancel, or whatever's not under it. Okay, what do we do next?
And x's that make 1, 0.
Yes, the method of creating zeros, calculus books like to call it. So we set x equal 1. So we get, so this term will go away, and then we'll get b times minus 1. B is minus 1. Set x equal to 2. So you get 1 is equal to, so this term will go away, and it'll have a times 1. So a is equal to 1. So a partial fraction decomposition is 1 over x minus 2 minus 1 over x minus 1. Okay. So now what we have is fractions that can easily be written as sum of a geometric series. What we're gonna have, we're gonna have a difference of geometric series. Oh, that's a beer weather alert, because we can't go through a week without having one of those. Oh, for tomorrow. Oh, great, 3 out of 5 risk, fantastic. Okay. Okay, so now work as a function in this form, to write it. PowerSeries. So we have 1 over x minus 2 minus 1 over x minus 1. So like before, I need to have the fraction where I have 1 minus something in the denominator. So in the first fraction, I'm going to multiply and divide by 1/2. And then I'll write this fraction as plus 1 over 1 minus x. That one already is in the right form. Okay, so I'll have minus 1/2 or 1 minus x over 2 plus 4 over 1 minus x. So for each term, we're going to have separate a's and r's. So for the first one, a is minus 1/2, r is equal to x over 2. And for the second one, a is 1 and r is x. So for the first one, we're going to have the sum of a times r to the n plus second one, a times r to the n, so 1 times x to the n. What I want to have is one power series. So to combine them, I want to write this one as this some constant times x to the n. We're going to have minus 1. Then I have 2 to the n in the denominator, and then a number 2 here, so that'll be 2 to the n plus 1 x to the n. And then I have plus 1 from over here. All of this times x to the n. And I'm done. That's my series. But we have to be careful about versions.
What happened? Where's the 1?
Sorry, what?
The plus 1.
Oh, I came from here.
Okay.
Because these series converge under different circumstances. This converges if the absolute value of x is less than 1. Whereas this one, we have absolute value of x over 2 must be less than 1. So absolute value of x must be less than 2. But remember what I said earlier about when you combine series, if you're combining two series that converge, then the sum converges. If one converges and the other doesn't, the whole thing, the sum will diverge. So we have to use a more stringent condition. So this converges if and only if absolute value of x is less than 1. Any questions about how this one played out?
How did you combine the series?
Well, because they're both going from n equals 0 to infinity, I can just add these. And then I factored out an x to the n. To get coefficients. If you start at different points, then you can't really combine them until you use an index shift on one of them to bring them in line. Okay. This last example, I'm going to go the other way. Start with power series. And find a function that it sums to. Still using a formula for a geometric series. So we have sum from 1 to infinity, 1 over x minus 9, all raised to the, let's see, 2n minus 1. So it's sum of odd powers of 1 over x minus 9. So I want to get this into a form from 0 to infinity of a times r dn for some a and r that can depend on x if necessary. So first thing I'll do is because notice I've written the sum here starting at 0, but this one starts at 1. So I'm going to start off with an index shift. We'll start from n equals 0 to infinity. Now, because I am decreasing the starting value of n.
Oh wait, is that x minus 9 to n minus 1?
Yeah, x minus 9 all raised to the 2n minus 1 power. So because I'm decreasing the starting value of n, in here I need to replace n with n plus 1. Bless you. So I get 1 over x minus 9, all raised to the 2n plus 1 power.
Wait, can you say that one more time?
However, so because I'm dropping the starting value, in here, wherever you see n, gotta replace it with n plus 1.
Okay. Wouldn't it just be 2n?
No, because 2, you have 2 times n plus 1 minus 1, that is parentheses.
Okay.
Okay. All right. Okay. I still want this as the expression, something raised to the nth power. So what I'm going to do is, besides x minus 9 to the 2n plus 1, I'm going to take one factor of x minus 1 over x minus 9 and write it separately. And then what's left is add 1 over x minus 9 to the 2n. But then I can write that as 1 over x minus 9. And then the other fraction will be x minus 9 squared, all raised to the nth power. Actually, I can write it this way. All raised to the nth power. Now it matches the form that I want. Is a geometric series where A is equal to 1 over x minus 9, and R is equal to whatever's being raised to the nth power. So that's 1 over x minus 9, the whole thing squared. So now I can apply the formula, A over 1 minus R. So I'll have A up top. And then down below, I'll have 1 minus 1 over x minus 9 squared. So rather complicated fraction. So the easiest way to make this in a nicer form is if I multiply top and bottom by x minus 9 squared. So up top, I have x minus 9 squared over x minus 9, so that's just x minus 9. And then down below, I'll have x minus 9 quantity squared minus 1. So this is my function that's represented by this power series.
Wait, just check that 1 over x minus 9 squared, that's the power of?
Of this,
No, right, there, that,
n.
okay.
Actually, the original series doesn't really meet the typical definition of power series because it's negative powers of x minus 9, but sort of swept it under the rug. We still get a function from it. But because it's negative powers of x minus 9 in the original series, the convergence behavior is rather odd because I need this to have absolute value less than 1. So this converges if absolute value of x minus 9 is greater than 1. You can see here, absolute value of x minus 9 equals 1, so like x is equal to 8 or 10. This is undefined, I'm defining by 0. As long as x is outside of that range, this series will converge. One of the homework problems is like this one. Some of the other examples I did earlier today are also based on homework problems. Questions about how this one played out? So the basic idea, whatever you have, force it to be a geometric series in whatever way you can.
Less than 1.
No, if you like do the algebra, it's greater than, just because.
Yeah, because it's x in the denominator. For example, suppose x is like 100, let's say, then r is going to be a lot less than 1. All right. Well, we seem to have a lot of time left. How unfortunate. So there's time for homework questions if anybody has any.
I don't have questions yet, I'm just like.
Okay. See any in the chat either. Next week, we'll only have class on Wednesday due to Mardi Gras break.
Oh, when is the homework due next week?
Okay, so, yes, the 20th, yes, so a week from today.
Okay. For me, I was thinking this Monday might wait a second.
Oh, yeah, I wouldn't have something to do over Mardi Gras break.
I have a feeling some teachers will.
Oh, boy.
I think we're not allowed to.
That doesn't mean they listen.
But,
It might not.
yeah, it's something that the administration has made some noise about, that they have made it very clear that they do not want that, so, if, but the thing is, I think, professors who do that sort of thing, they count on students not saying anything or complaining above, and if they do, then, but something like that, if you go to the, like to the provost office, then everyone's would come down on a professor like a hammer, so.
We don't have a lot of work to do over the break. I have a lot of work to do right after.
Yeah, I guess when, I guess what I'm doing. Oh, is there a question, Morgan?
Linda, but it's a silly question.
Okay, well,
Okay, so integral test, right?
yeah.
So once we know we have three rules, we know it's converging.
Yeah.
So I think I just get confused on what value we're supposed to be putting in to like where it equals.
You mean like where to integrate or?
Yeah,
Well,
like does it, ouch.
the only thing that really matters is that the upper limit be infinity. I think when I stated the integral test, I had the integral from 1 to infinity.
Yeah,
But for example, suppose a function is undefined at x equals 2, for instance. So as long as, well, the integral test requires that the function you're integrating has to be continuous and decreasing. So you can start the lower limit at anywhere that's convenient
Mhm.
to avoid any like vertical asymptotes or whatever. So as long as there's a clear path from wherever you start off to infinity, you're good. So I'll be working over Mardi Gras break because I have to, for the following week, which is when I won't be here, I have to record those classes in advance, and then I'll also be getting the practice midterm ready, so so by next Wednesday, I'll have that posted.
I think you're not here. Did we just watch the lecture?
Yes, yeah, you don't come here. But certainly send me any questions you might have. Yeah,
How would you do arc tangent evaluated at infinity?
okay, so. All right, it's really what that means is you're checking at what angle does tangent go off to plus infinity. And that would be at pi over 2. Now arctangent, the range of arctangent consists of angles between minus pi over 2 and pi over 2. So that's why that's the angle you choose. So that's how arctangent of minus infinity is minus pi over 2, and then plus infinity is pi over 2. Yeah, unfortunately, there's not a more systematic way to get it. It's just an understanding of how tangent behaves.
You're gonna give us a paper, like practice, exam practice, right? Or test?
Okay, I'm gonna post in Canvas a practice test and the solution to a practice test in a separate document.
But it's not gonna be like the homework. It'll be actually formatted how our test is.
Yes,
Okay.
yeah, it's exactly the same kind of document, just I think it was changed. I'm trying to remember, I'm looking at like, well, it's been a long time since I've done one of these tests for Cal 3. Oh, okay. I did not have a formula sheet. Well, if there's any formulas that are necessary, I'll be sure to include them. If I don't want to have these spending your time memorizing, then I'll include them. But it's up to you to know the convergence tests. And that's something else I'll be posting, a study guide that lists all the tests for convergence of sequences in series in one place. Yeah,
Can you look at this with me?
okay.
I'm still confused. I'm gonna just say it. So I know convergence.
Okay, it's not gonna be series, you're actually evaluating the integral.
Okay.
So you're taking antiderivative of e to minus 4x. And then plug in x equal to 1. And there's not gonna be any n in that answer.
Okay.
Alright. Anything more? Well, also I'll stick around in case anybody has individual questions. Alright. Grant,
Once you're in it, can you come again and help me?
okay.
I think I'm fine.